Well, hello, this is John Perham here. There's me and there's my email address, and I'm going to talk about the solution to this week's tutorial problem. That's week 4 in the course MATH1231 Algebra. But before I do so, I want to say something about the computer algebra system Mathematica, vectors and matrices, because I use Mathematica for virtually all symbolic, graphical and numerical computations, including solving the tutorial problems. But one aspect which needs getting used to is the way Mathematica handles vectors and matrices. The elements of a vector are stored in a linear list, such as the vector R, which I can establish using that. So, the elements can be addressed by their position in the list, which can be seen using this. So the second element in the list is Y. And a matrix in Mathematica, or the elements of a matrix, are stored as a vector of vectors. So there's the first row, and there's the second row, and the third row. So we'll establish that. And it can be visualized in matrix form using this. And we can address the element of a matrix by its position. So this would be the element in the second row and third column using this. And that's 6, as we see here. And there you go. Now, if you want to calculate the product of two matrices in Mathematica, then you do this. You just multiply the two with a dot between them. And we can show that in matrix form using that. Well, let's compare that with the form for the usual form for the product of a matrix. So for each row and I and each column j, then I take the sum of the product of the kth element in the first row, in row I, with the kth element in column J, and I make a table of that and I present it in matrix form, and you can see that that's exactly the same as what we had here. So the ij element being the scalar product of the ith row of the matrix, which is the first row, and the jth column, which is this one here. Now, in MATH1231, vectors are represented by column matrices, which we can do using this. So this presents the elements of the vector R in this column matrix form. And we do that because the result of multiplying the vector R by the matrix A can be written down and done manually to give the result. So A times R, we take the matrix A and then the column vector R, and then the first element is the scalar product of the first row with the vector, the column matrix, which is this, and so on. Well, the same corresponding multiplication can be carried out by Mathematica using this. So we just multiply the matrix by the vector, and you can see, we'll see in a minute, that this can be visualized in matrix form like so, and it's the same as we got up here. So confident that Mathematica carries out matrix multiplication correctly, we will always visualize our vectors as column matrices, and we'll need a generic tool for that. So we construct this function here, v2 cvec, whose argument is some vector and it's precisely this form here. So we can test that little tool using this. Well, first of all, got to establish it. So let's do that, and then when we do that, it gives the right answer. So let's get on to the problems now. And the first problem, problem 40, is about polynomials. So the question is the polynomial, which we can construct using that, in the span of the polynomials which can be established using that? So we've got these three polynomials, like so. So let's get to the solution. Our strategy is to first convert the problem into a problem in linear algebra, then solve the set of linear equations, and finally use the solution and our knowledge of linear algebra to answer the questions. So, so the first part is derivation of the linear equations. Well, the vector P will be in the span of these three vectors here if we can find some linear combination of these polynomials such that it's equal to P of x. So let's, in other words, we have to find values of some parameters a, b and c, and then in such a way that the polynomial formed by multiplying a by the first polynomial plus b times the second plus c times the third, and then subtracting off the polynomial p of x, that should be the zero polynomial. Well, this will be the case if all the coefficients, the coefficients of all powers vanish. So let's calculate those. Well, first of all, let's establish this polynomial there, and we need to calculate the coefficients of the various powers. Well, there's a mathematical function called coefficient, which takes as input some object and then produces the jth power of the variable x in that expression. So we want to do that for j equals 0, 1 and 2, and they will be the coefficients. And these have to be, if our polynomial is going to be in the span, then these expressions should all be 0. And we can see that that's a set of linear equations for the parameters a, b and c. So linear equations, we want to find the coefficient matrix. And to do that, we find the coefficient of the jth variable a, or the first variable a, in the first equation, and so on. So again, we use this coefficient function, and we'll get this collection of coefficients, and then we can express that in matrix form using this. And to calculate the elements of the right-hand side vector, we can do that by taking the product of the coefficient matrix with the vector of parameters and subtracting off the coefficients. So we do that, and that's the vector 1, 1, 1, and we can visualize that as a column matrix using that. So we've reduced the problem to finding the solution of that set of linear equations, and we do that using row reduction. So to do that, we need to construct the augmented matrix, and to do that, for each row of the matrix, we add the corresponding element of the right-hand side vector. So we can do that so that that's done by the matrix function join, which joins two vectors. And there it is, and we can visualize it using this. So we want to do row reduction on that, and we want to do it quasi-manually, so we can see that we want to get zeros in the, oops, here and here. So we add the first row to the second row and subtract twice the first row from the second row. And we can do that by forming a new augmented matrix whose first row is the same as this one, whose second row is the sum of the second and the first row, and whose third row is the current third row minus twice the first row. So we do that, and we can visualize that as a matrix, and we can see that indeed we've got vectors here, or sorry, zeros here and here. Well, we now carry out the second phase of the row reduction by adding 3 times the second row to the third row, keeping the first 2 rows the same, and we get that. And we can visualize it as a matrix using that. Now, what can we see? Well, we can see that this column here is non-leading, and in fact, if we express the bottom row as a linear equation, it says that 0 equals 5. And we're not prepared to accept that, so we conclude that this solution has no, or this set of linear equations has no solution, and therefore p of x is not in the span of the given polynomials, which must be linearly dependent.